Hi there. So I guess I'm going to wait until it's actually whatever time it is for the tutorial in your time zone. But if you have questions or requests for the tutorial at this time, then feel free to put them into the event feed. Where I hope I'm going to be able to find them. Otherwise, I'm just going to sit here for a moment longer and you can watch me drink my tea. So we'll just give it like 2 extra minutes in case you want to also grab a drink or something, and then we'll start. Okay, I guess it is time. So welcome. My name is Mike Sperber, and I'm here to tell you a little bit about how to teach functional programming. So it's a tutorial that I've given many times before at ICFP and elsewhere in different forms. It works best, as I think you'll find out, it works best if we're having a conversation rather than just have me tell you, what to do. That's going to be a little bit difficult on this platform. We'll just try to manage somehow. I think the way that I'm going to try structuring it is I'm going to give you an introductory talk with some introductory remarks. And as you'll find out during that talk, I'm going to try to tell you that teaching is often done completely wrong. And so hopefully those, my opening remarks will spark some controversy. And a more important, one goal for this tutorial can be that I teach you or I tell you about how I teach, and that's fine. But I think a more worthy goal would be that we're having a heated discussion about really what makes teaching go well and what doesn't make it go well. So it's really important to me that so a lot of the things, some of the things that I'm going to say might be controversial in some sense, or you might think, how can he know this? How does he know this? That's wrong what he's saying. Really, teaching something else is true about teaching. I would like to really ask you to voice, that opinion, either via the chat or preferably at some point by raising your hand, and then we'll try to bring hopefully lots of people on stage, and we'll see how that goes. Okay, so that's very important, I think, for a lively conversation, that you don't just go, I'm in Mike's tutorial, therefore we're just going to go with what he says, but that if you hold different opinions, or if your experience shows something else, something that's different from what I say, that we're having a conversation about that. And I think that's when this tutorial works best. Okay, we'll see how that goes. Unfortunately, on this platform, I feel like I'm talking to a wall, so I'm just going to start talking, and we'll see how it goes, and somebody's going to have to interrupt me if it's supposed to go in a different direction. So I'm going to try to share a bunch of slides with you. Here they are. Hopefully, should be coming up. Anyway, so let me tell you a little bit about my background. So I've been teaching programming for a very long time, probably longer than some of you people are old. So my first official computer science or programming class is something I taught at the high school level in 1987. So that's a long time ago, but I've taught it at the University of Tübingen for many years, done the introductory programming class for computer science majors, also for computer science minors. I've also taught to humanities majors. That's an interesting experience. And for the past almost 10 years now, I've mostly been doing professional training. And of course, if you're kind of a lifelong educator, then everybody around you suffers a little bit. So my kids occasionally have to suffer, or other people's kids, my goddaughter, co-workers, people are, among my friends who are interested in programming. All kinds of people have to suffer through my trying to teach them how to program. And I'm going to try to tell you something based on that experience. Give you a little bit more of my current background. I'm CEO of a company called Active Group. We do software project development using lots of different functional languages. So I'm really, even though it might seem that way, I'm really not particular about one, functional language or another. We also run the leading German language blog on this. We also run a conference. If you were here for ICFP 2019, Bob was co-located with that, or a special edition of Bob, and we're doing that again in 2022. Hopefully in Berlin. We'll see how that goes. I think Bob was a great match for ICFP, so if you like it here, it's likely that you might also enjoy Bob if you can make it there. So let me start by asking a question, right? If you're from the OCaml camp of functional programming, do you love OCaml? Is that something you feel emotional or excited about? Or, do you love Haskell? Or it could be, you do. So it could be lots of, whatever your functional programming language is, you probably feel excited about that. And, lots of people have gone to that place where they say, this language resonates with me. And they conclude from that, because it resonates with me, it also has to be an appropriate tool for teaching. And so, for example, one very popular and very influential place where that happened was MIT in the 1980s, where there were a bunch of people who loved Scheme. They were really excited about the functional programming language Scheme. And they concluded that because we like Scheme so much, it has to be a great tool for teaching. And they had good reasons to support that view, because Scheme is this language that has very regular syntax, so there's not a lot of material to learn there. The language is very small. It's functional. Of course, that's great. It's easy to transition from Scheme to any other language. And what could possibly go wrong, right? And this book that came out of that you might have seen, the Purple Book, or the Wizard Book, as it's sometimes called, was very influential in its day. And it's a great book. You should probably own it. But unfortunately, it's not a great book for teaching, or at least it's not a great book for teaching beginners. And I'll try to tell you a little bit about why that is. So here's an example. Most people find that book very compelling. If you're not among them, sorry, there's probably other books. Here's one person who didn't find it very compelling, Phil Wadler, who's probably around at ICFP somewhere right now. And when the book, The Wizard or Purple Book, came out, he published a critique of that, and he said, well, for teaching, really, scheme is the wrong language. I'm more excited about a different language. You might be tempted to think it's Haskell, but this paper is so old that Haskell didn't exist yet. So the predecessor of Haskell was a language called Miranda. To the intents and purposes of this talk, think Haskell there. And Phil Wadler wrote in this article, here's 4 language features that are great in Miranda, pattern matching, whatever, 4 things. Typing, of course, and those 4 features, they're great. I love them about Miranda, and therefore they also are going to make teaching better. And unfortunately, that's a frequent fallacy. So I hear already, Haskell does not look like a language you should teach for undergrads in the first FP class. Lots of people do that, though. I highly recommend against that. Haskell is a great language. I do lots of work in Haskell, but so we'll get to that. I'll try to explain why that is. Anyway, so why would you be tempted to think that? And here's the reason, right? You teach your favorite functional language that you're excited about. You are going to convey that to your students in class, and some students will pick up on that, right? And so you teach, whatever it is, Haskell, OCaml, Scheme, it doesn't really matter. And inevitably, you do that long enough to enough students, some students will come up to you and say, oh, Dr. Sperber, in my case, or whatever, they'd say, Dr. Sperber, your class is wonderful, right? And this Scheme thing, or this Haskell thing, or this OCaml thing that you're doing, it's great. It looks great, right? It's wonderful. I love it. I think, you're the perfect teacher. And I think you're going to feel gratified about that. And it's easy to convince yourself, because students are coming up to me and telling me how wonderful my class is, and how wonderful functional programming is, and how wonderful programming language X is, that these all are the appropriate tools for teaching. And unfortunately, that's a fallacy. And one reason why it's a fallacy is this. Well, your students are typically not like you, or they're not like Eugenia Cheng, for example, if she's teaching. And I'm sure she's keenly aware of that. They're also not Simon Peyton-Jones. So just because you're Simon Peyton-Jones, you love the language that you've been working on for many years, doesn't mean it's an appropriate tool for teaching. I don't think Simon ever said that, but we're just going to go with that. More importantly, it's not just the difference between the expert and people who are not experts. So the thing is this: cognition, the way that your brain works when you're learning about something, it changes as you learn more about a certain subject. And this is a quote from a great book on education called Why Don't Students Like School by a guy called Daniel Willingham, which I found extremely illuminating. And he has these headline chapter banners where it says, so one of them is cognition is fundamentally different early and late in training, which just means that literally when you think about functional programming, your brain works different from the brain of your students. And that means just because something seems compelling to you does not mean it is as compelling to your students. There might be a few Sheldons or whatever, right? Those are the ones that will come up to you and tell you how great you are. But you will find out that inevitably there's lots of students there who don't find your material so compelling, or who struggle. I'm going to tell you a little different story from a domain outside of functional programming, which I think is informative here. So, lots of people, of course, have thought about how to teach, kids, students, young students how to program. One of them was a guy called Seymour Papert, who's developed a programming language called Logo, which you might remember or might have heard about. And Papert didn't just think about programming languages for kids. He had a very holistic view he had an educational philosophy, if you will, called Constructionism. And the idea with constructionism, I'm abbreviating greatly here, is that, well, you just give a kid access to material and information, and and the kid will just teach themselves, right? They will figure it out. They're motivated. They're curious. If you just give them access to the material they think they need, there's no need for a classroom. So Seymour Papert really, really hated classrooms. So that's such a charming idea, right? And it seems very, it's just a compelling idea in and of itself, right? It means that people are self-determining in what they want to learn about. They can go at their own pace. All of those things that sound very wonderful about how to learn something and how to teach. Also, it seems like it would be a lot less work for the teacher. So that's also charming about it. And of course, Papert's work was extremely influential and continues to be very influential. And I think one informative example that's recorded is the Smalltalk folks, right, who worked on Smalltalk in the 70s, and they heard about Logo, and they heard about using a programming language to teach kids. And they figured, well, this is a great idea, teaching programming to kids. On the other hand, this Logo thing, we're excited about Smalltalk. So we're just going to try the exact same thing that Papert did with Logo and with kids. We're just going to try it with Smalltalk and with kids. And so, they looked around for a couple of unsuspecting kids to teach Smalltalk to. And, sure enough, a couple of the kids came up to them and said, this Smalltalk thing, greatest thing ever. You're such great teachers. This is all wonderful. But really, to their credit, the Smalltalk folks then looked a little closer at what was happening. And they noticed two things. So first of all, they noticed that that most of the kids, of course, that they recruited, they were doing this at Stanford, so in Palo Alto, and the children were of course chosen from their neighborhood, from Palo Alto schools, which is very wealthy, and so we have lots of students from a pretty well-to-do, well-adjusted background, and not just that, even among those well-adjusted, wealthy kids, only a few of them actually took to that material naturally. And most of them really, really had to struggle. So what I really want to press upon you, it's really, really easy to fool yourself that your approach to teaching is working well when in fact it is not, or it's not in the sense that maybe some of your students are doing fine, but more of your students are probably not doing fine. You might have as your goal, I primarily want to teach, or I want to figure out what the smartest students are, and I want to teach those, and so on. And that's an idea that was propagated a lot in the 80s when people were dealing with this book by Abels and Sussman at MIT, that people thought, this approach works very well for the students at MIT, but we're just not MIT, so it doesn't work that well for us. But even MIT has abandoned this approach since, for good reason. So one result from constructionism was that you might have heard about was the one laptop per child project, right? Which the idea was to give computers access to material and information to kids specifically in the third world, and they will just figure it out themselves and teach themselves. And in the aftermath, the old PC died for various reasons, and lots of studies I think have been done in the aftermath. Here's one that I found very illuminating by Morgan Ames, who specifically looked at how well the educational approach of OLPC actually worked. And one problem is that, again, the goal was to reach a wide variety of students, specifically to bring education to kids in the third world, and thus bring some diversity to this computing field. The means of constructionism are not really an appropriate way to do that, right? Constructionism does do some things well, but sort of teaching in breadth is just not one of them. And predictably, the project failed at this particular goal. So, why does it fail? One reason for that, here's another banner headline from Willingham's book, is people are curious, so they get easily excited about new stuff. But when that new stuff happens to be a complex activity, such as programming, it's just hard work, right? And people don't take naturally to hard work. People are not naturally good thinkers. It's work. And so with lots of lots of people, this teaching themselves approach kind of comes to an end at some point before you've reached your goal, right? And this constructionism idea, it's very present still in today's tools. So here's a great tool for sort of for experimenting with programming, the Scratch programming language, which has this blocks model where you have to fit blocks in a certain way, which is kind of like a type system for statements. So I guess this is the modern day version of Logo. There's even a functional version of that based on Scheme. These are great tools for digital storytelling. They're not such great tools for actually learning how to program. And that's an important distinction to understand. Now, you might conclude that it's not really the tools that you're using, but really that you have to be more actively engaged in your teaching activity because, well, here's another banner headline: intelligence can be changed through sustained hard work. I'm sure you've come across this idea, or this empirically validated idea. It's not just an idea that through if you want to get better at something, it's a good idea to do directed practice. So that is sustained hard work. So if you work hard on a particular subject for longer periods of time, you'll learn about it. And educators across the world have taken up this idea, and in a lot of places, in Germany at least, there's lots of educational initiatives that try to foster this idea of getting kids to do sustained hard work on a subject that will eventually lead to programming, and it mostly involves robots. And I'm sure you've seen an educational initiative in your neighborhood, in your country, or in your state that just says, well, we're just going to introduce robots in the classroom. That's going to get kids excited. That is going to get kids want to spend a lot of time with robots, and that will make them learn. And the thinking is not quite wrong, but it's pretty wrong. And one reason why it's wrong, one reason why it's wrong is that also it tends to attract mostly those well-adjusted, the Sheldons again. Another one is, here's another banner headline: memory is the residue of thought. So when you're dealing with robots, you think about robots all the time. That's where you put your hard work. And but if you're really trying to teach kids how to program, then they're spending most of their time on robots, not on the programming bit. And again, it works predictably poorly. So that's why a lot of educational approaches, I think, are failing. But there's more reasons. So here's one that I call learning by example. And again, I'm going to try to do this low risk here in FP community. So I just have a Java example or a Java book here. So it says learn Java the easy way, right, from 2017. And the way its teaching approach is based on examples. So what it says is, well, we're going to do we have an example problem, and we'll show you how to solve that example. So in this case, it's the high-low guessing game, I guess. And then it says, well, in order to create a while loop, we need to insert a while statement before the last 3 lines of code. So it shows the steps that are needed to actually implement that example, but it doesn't tell you anything about how to select which step to take next. So there's the world of the problem, and then there's the statements and syntactic forms available in your programming language, but they're only connected through examples. And the expectation is that you've seen a couple of examples how to program, and somehow magically you will then be able to program your own stuff. And my experience has very consistently been that it works with a few students, but does not work with most. And the result is 2 things. First of all, a lot of students just get frustrated. If you look closely, they just do not manage by themselves to successfully write substantial programs. And moreover, even those that do succeed in constructing substantial programs, they've taught themselves the programs often look like the spaghetti wires that you see on the right, because there's no systematic approach to that. So, if you think, oh, well, that's the Java book, you will find lots of books on that try to teach functional programming work in exactly the same way, either through this learning by example approach, where there's just a bunch of examples, and then you're supposed to somehow magically infer how to do other programs, or even worse, if you have books that are just grouped by programming language feature, and then expect you to somehow, by understanding how the programming language feature works, you're also supposed to be able to apply it then to your problem, and it just doesn't work. in my experience. So let me summarize a couple of common mistakes. So one mistake is that students are like us because we think we're excited about something. Students also need to be excited about it. What I love must be great for teaching. A common mistake is that students will somehow figure it out themselves. Often, I don't know, depending on where you live in Germany, you often hear politicians talk about education in a way that, oh, we just have to get young people excited about STEM or computers or programming, and then then we'll have a future generation of software developers or something. But there's some steps missing in the middle. Getting excited about something is not the same thing, and it doesn't automatically lead to competency in that area. In particular, excitement is a very poor guide when you're trying to do your learning or your teaching in an equitable way, where you provide access to the abilities that you're trying to impart to a wide variety of students. Does that make sense at all? I'm hoping it does. Okay, I'm getting people are there. Thank you. Feedback is great. Okay. So, and that means that if you're I started teaching. I mentioned I started teaching in the 80s, right? And I made all of those mistakes that I listed, right? All of them multiple times. And so it's a bitter insight that the stuff that you feel most excited about just does not work in the classroom. So at one point I put up this poster. It's actually hanging in my office. This is a photo from my office. So stuff, educational approaches to teaching that don't work, you need to get rid of them somehow. And it's that can be a very disappointing and sinking feeling when it happens to you in the beginning. You learn how to appreciate it more later, but it's certainly disappointing when you've spent a long time on preparing some educational approach or some book or some chapter in a book, and you find out that it just does not work in practice, and then it's time to do something else. I think one question might be in order at this point. What are we trying to teach, right? We're saying we're trying to teach how to program, but what does that really mean? And what I want, so it might mean you're teaching some digital medium for expression, right? That's, I'm not going to talk about that. That's, Scratch and Snap are great tools for that. It might mean, so what I really want to do is I want to build houses, right? Something that requires substantial structure, and that is hopefully going to meet users' needs, where I have this idea in my head and I want to translate that idea into a robust working piece of software, right? And so that's what I'm trying to do. And I want to teach students to be able to do that by themselves without the help of an educator or a senior developer or something like that. So, somewhat belatedly, I thought about, did anybody ever teach me a substantial activity in the sense that I didn't teach myself, right? And eventually I realized, well, the first time it really happened to me was when I spent a year as a high school junior and as an exchange student in the United States in English class. And so this is my English teacher from 1987, Anne Carvalho. And she handed out this sheet of paper in the first class, and it's probably too small, so I've zoomed in here. Hopefully you can read it now. And what it said at the beginning, it says, well, during this class, you're going to write a lot of compositions, or you're going to write a lot of papers about literature. And here's a guide to write a composition. And then it provided, what you see here. And if you look, it's like an outline for a composition. So it says, so here I've zoomed in on the second part of the outline. It says the body of your composition. It says usually it's 3 paragraphs, with each paragraph developing one of the areas of the thesis. And then it gives you an outline for that paragraph. And so if you look at that outline, it pretty much tells you your composition is going to have like 5 paragraphs. I think it was 5 paragraphs. First paragraph has this purpose, second one, this, third, this. And, in particular, this paragraph, it consists of a bunch of sentences. The first sentence does this, the second sentence does that, the third sentence does this. And I invite you to think about how that makes you feel, right? You're sitting in English class, or you're sitting in programming class, somebody gives you a handout like that, right? Does it feel overly patronizing to you? it certainly felt to me. One reason maybe was I'm German. Germans tend to not take well to this kind of this kind of teaching. I was an instant rebel when I got that handout. I was like, I don't need a stinking handout. I can just, I can write a composition, any day I want. I don't need an outline to do that. And it took me a while to realize that this was extremely helpful, not because it's the only way to write a composition, but because it's one way that's proven effective. And it's extremely, so this really, not in the sense of constructionism, but this is a constructive approach, because it really says, here's how to write a composition, right? You have this outline. Now you have to write a sentence that does this. And so it's broken down to a degree where it's possible, again, for a wide variety of students, at least in my class, to be able to follow those instructions and write a composition successfully. So anyway, so here's kind of a break. So that's what I've been thinking about. Another thing to think about is this, right? I think it's become popular when we talk about education is to stress the individualistic aspect of it, especially I think in the past year, where everybody's learning online or is learning from YouTube videos or something like that, and we've come to appreciate that everybody's going at it at their own pace, looking at the material that feels most appropriate to them. And of course, again, it feels very empowering to say, everybody's different, right? And this particular approach of learning is going to cater to your individual needs and strengths and stuff like that. However, when it comes to learning, children are more alike than different in terms of learning. I think we like to think of ourselves as kind of unique in our learning style. We think, oh, I learn this way, somebody else learns that way. What works for you doesn't work for me. But, empirically, that's just not true. Kids generally all work, children's minds or learners' minds generally work in pretty similar fashion. And there are many more similarities than there are differences. And that also means that, if you have an effective approach for teaching, magically, then that you have a good chance of that applying to a wide variety of students. And it also means that the good old classroom probably still has some value in that it kind of forces people into that sort of social activity of learning, where everybody's going at their own, where everybody's going at the same pace and is looking at the same material together with others. So out of that idea, this was not my idea. I should really say. So the group of Matthias Felleisen back then at Rice University was thinking about teaching very hard, and they eventually came out with a book called How to Design Programs. It's you can download that or you can at least look at it for free on the internet. And you can, if you happen to be German, I don't know if there's any German-speaking people here. We did a German language book, which and the current edition is hopefully going to be done in a few months. But you can get the current draft also for free from that website. So How to Design Programs, primary author is a guy called Matthias Felleisen, who might also hang out here at ICFP or not, I don't know. And he developed an approach that is very similar to that outline for compositions that I showed you earlier, but it's called design recipes. And so if I'm going to tell you something about teaching today, it's going to be about that, about design recipes. But Matthias's group did a lot more. They also developed specific programming languages for teaching and also a programming environment that's called Dr. Racket, formerly known as Dr. Scheme. So you can see that they also started from that Scheme place. And I'll show you more about that later. So this Dr. Racket programming environment really caters in many ways to the needs of learners rather than to professional programmers. So here's, again, an important difference to understand that your learners are not professional programmers. And there's an interest, I'll talk about that later. So over the years, what we've done, what Matthias's group has done, and what we've done over the years is developed a set of teaching languages that grow with learning, that provide feedback that works particularly well for learners, that maps to the design recipe pedagogy that I might talk about later. And this really is the most important part, has been iteratively improved over many, many years, right? And I can't stress that enough, how important it is not just to kind of develop material that feels compelling to you, but really evaluate how it does in the classroom and how students are coping with that. And then if particular aspects of that don't work particularly well, you try to improve it. And then you repeat that same cycle. And that's what often does not happen sort of in the current educational machinery. So the pedagogy, and that really, if you've heard me talk about constructionism earlier, that pedagogy goes against most of the tenets of constructionism, I guess. It is based on something called, that I'd like to call systematic design. So it's an explicit methodology that is called design recipes, and it stresses form over function. And remember that English composition outline I showed, it's similar to that, right? It really stresses that your program or your function, it has to have a certain shape. And we're not just looking at, does it work correctly? We're also looking at its shape. The pedagogy has been also iteratively improved over many years. Many publications have come out of that. And in particular, somewhat counterintuitively, it does not stress at all excitement or getting people into positive feelings about the material. It is unbelievably pedantic and bureaucratic. So here in Germany, I like to call it the German bureaucrats' approach to teaching how to program. So it's very, very different from constructionism and from example-based learning and from lots of other approaches to on teaching how to program. And if you look at that book, and this is really why we need to have oh no. Well, usually when people have looked at this book, How to Design Programs, it's a book that's really, really hard to love because it is so pedantic and so boring, I think, in many ways, right? Somebody seems to like it, that's fine. I like it too, but I very distinctly remember looking at it when it first came out, and I was thinking, this is so boring. I'm never going to, I can't imagine myself taking that to my students. And so it's not, I think for educators, it's not a very compelling book. And the reason for that, it's not aimed at educators. It's really directed at learners. So, and in particular, one of the reasons that why it's so boring and so pedantic is that it's based on these explicit name techniques, and that it does a lot with sort of mechanical derivation of program fragments and stuff like that. And if you want, I'll tell you more about that later. Let me give you a very brief outline. Let me rush through that. If you're interested in that more, we can cover that at length in the rest of the tutorial. Don't be scared by the fact that some of this is in German. It just happens to be from our material. But I'll continue doing this in English. So in particular, the design recipes stress something called data analysis. So taking a systematic look at the data, you're describing your problem domain and deriving from the description of the problem domain appropriate data structures via a taxonomy of data. And that's kind of at the center of design recipes. And once you know the shape of the data, substantial parts of your program, of the structure of your program, are derived mechanically from that. So that's what makes it super boring, because you always say, well, when you see data of that shape, you always write a function, this particular shape that's derived from the data. And again, if you want, we'll do much more of that. So let me contrast these two things, right? Just to really try to make that very clear, because even, if you haven't really taught using how to design programs or design recipes before, I promise you, even now, you're underestimating the amount of tedium and bureaucracy and, pedantics involved in it. But I can tell you that we've had a lot of good experiences using that in the classroom. So, so the approach behind how to design programs is something called program by design. And the most substantial differences are these, right? Is constructionism really is a fundamentally individualistic approach to teaching, whereas program by design turns out to be equitable. It brings the material equally to a wide variety of students. I'm not going to say all students, but most students can actually learn how to program using this approach. Constructionism focuses on providing tools and materials. Program by design focuses on providing, instructions. Do this, do it this way. Constructionism provides lots of motivating examples. I'm not going to say that program by design does not provide motivating examples, but mostly since it's based on functional programming, it's also in the vicinity of algebra, and so we can. There's lots of good benefits between algebra and programming to be had from that, and we focus on that rather than fun examples that we might have. Having said that, the teaching languages that come with Dr. Racket do include a really, really nice library for constructing graphics or pictures or images, and then animating those images. And you can animate those images into full-blown video games. And that's usually an exercise that we run at the university level during the intro course. So this approach, it's how to design programs first came out in 2001. So it's been around for literally 20 years now. And we've also been teaching that approach for around 20 years in different contexts. One context where it also works exceedingly well is the Bootstrap project, which at its core creates a connection between programming and algebra using the same approach. Very successful teaching high school kids how to program. And paradoxically, I know I mentioned that at the beginning. These days, I mostly teach professional programmers and professional trainings that we provide. And strangely enough, when we started doing this, I thought, okay, professional programmers, they're aware of the oddities of professional programming languages and programming environments. So I mainly have to bring the pedagogy to them and just teach the same pedagogy, but using their favorite programming language or their favorite programming environment. Right? They come to us and they want training in F# or in Haskell or in OCaml. I could just teach using the design recipes in Haskell or F# or OCaml. And that turned out to work okay, but not great. And we've since moved to essentially for professional training using the exact same approach that we use for beginning programmers, just sped up greatly. So it's very fast. We sometimes run through that in 1 day or in 2 days, and which is 2/3 of a semester, I think, at the university level. And that also works exceedingly well. So for some reason, beginners in programming, professional programmers are here part of the same group when it comes to learning how to program. And they all come, and paradoxically, even though, or something that we were surprised at was that even though the approach is so bureaucratic and so boring and so pedantic, people, come out pretty happy once they figure it out. Oh, okay, I can actually, from the stuff that's been taught me, I can actually construct substantial programs myself. So let me summarize. If that is your goal, right, to teach equitably students how to construct programs that do substantial things, to construct them by themselves, our experience has been very consistently that you need to teach explicitly. It's not enough to provide examples. It's not enough to explain the features and constructs of your programming language. Also, you should use tools appropriate for beginners. Programming languages that are intended for professional programmers or for researchers, or programming environments meant for professional programmers, they do not work particularly well for beginners, and you can do better. You should improve iteratively. You should really try to evaluate how well whatever you're doing works. And if some aspect of it doesn't seem to work, try something else next time, see if that works better, and repeat that cycle. And that means really, and doing that, I should say, really is something that it takes long periods of time, and it's very expensive, because if you're teaching at the university level, it means wait until next year until you can run the next experiment. And therefore, I would strongly encourage you, that's what I'm going to try to do in this tutorial, is to learn from others. Lots of times I think people are going home, they're thinking, I'm just, this is all good and well, but I'm much more excited about this material, so that's what I'm going to try to impart on beginners. But I really encourage you to consider, that's why we need to have a conversation, to consider just adopting the approach of people who have gathered data and who've made improvements over many, many years. So in our case, over more than 20 years. And as hard as that is sometimes, it might mean saying goodbye to your favorite programming language, or goodbye to your favorite programming environment, or goodbye to your favorite chapter in somebody's book or even your own book. As hard as that is, If something doesn't work, get rid of it, try something else, rather than just imparting, causing pain for more generations of students. Okay. So that's all I have to say, at least in the context of this particular talk. And so now we can try to have a conversation. I see 13 people in the session. Is there a question or a remark that somebody would like to make? I think if you want to do that, you need to raise your hand somehow. I don't know how that works. And then I think I can ask you Q&A or just ask a question. Okay, Camilo asks, I'm going to read that question. How to balance the bureaucratic aspects, I think, is for the learners to have how to balance the bureaucratic aspects of the course for the learners to have a seamlessly experience and yet be interactive enough to be interesting. I'm not sure I see a contradiction between being interactive and between interactive and bureaucratic, right? Bureaucratic does not mean non-interactive. I think it means quite the opposite. It just means providing the same instructions, the same design recipes for everybody, and making sure that everybody uses them. In fact, when we teach, when I used to teach at the university level, I mean, when I do professional training these days, it's sometimes with 6 or 12, maximum of 12 people usually who are in the room. So it's very easy to be interactive with those. But even when we taught with 300 kids at the university level, it was, we had lots of aspects of the class organization that were interactive, but that were all, focusing on the same goal and using the same approach. Does that answer your question? Oh, can I push this button? I can show up. Now I understand. I can push a button and then it's displayed. Camilo, does that answer your question? You can, okay, so I can mark that as answered. That's how that works. Would somebody like to come on? So I sent a QA. Camilo, thank you very much. Anybody else like to say something or ask a question? Can you, the bootstrap slide, can I show that again? I can certainly try and do that. Give me a moment. Here's bootstrap. So Bootstrap is a project, or actually it's a project in the U.S. At the high school level, and so it's taught many generations of teachers, I think, in using that approach. Note that it doesn't say excitement and fun among the goals, right? It says equity, scale, rigor. If that doesn't sound boring, I don't know what does. Enzo, does that help? Do you have a question? Q&A. I do that. A student came to me, why should I learn if modern mainstream programming languages have a lot of functional features? What is your answer? Dimitri. Okay, let me show that question. Enzo says, thank you. So I'm going to mark that as answered. So I'll do this and show this on stage. Why should I learn Haskell, Camel, if modern mainstream programming languages have a lot of functional features? What is your answer? I think I have two answers to this, depending on who you're talking to. You can imagine, especially, I mean, we started teaching using functional languages in the late 90s, more than 20 years ago at the university level. And, back then, functional programming was way more of a niche than was even nichier, way more nichier than it is today. Very few people were doing functional programming. Professional programmers were basically not aware that it existed at all. That has completely changed by now. And students, so we would start class, we would start class, trying to provide a positive spin on this, right? We would say, we're using these funky languages to teach you because you're just better languages. And then we would give them reasons, similar to the slide that I showed you, why it's a better language. That never, ever worked. I don't remember a single student ever coming back and saying, oh, what you said convinces me, and now I'm totally on your side. That never worked. Eventually, we just switched to not giving reasons at all. right? And you notice that we're now using not just functional languages, we're using teaching languages. So these are languages that are guaranteed that students will never use them again. And so at the university level, we would just tell students that, this is just what you're going to have to deal with in this class, right? If you're not happy with it, fine, quit. We were really brutal about this. And I stopped providing positive motivation for functional languages at all. I'm not even sure we talked much about the fact that the languages that we were using were functional. We just said, we're going to teach you. We're the experts. You're the learners. We're going to tell you what to do. Here's how it's going to go. If you don't like it, you can leave anytime, but in order to get credit, you're going to have to do it our way. This was super, and your mileage might vary, but two things happened. First of all the complaints went away in our class. For some, even the official teaching evaluation, lots of students would, before we did that, would put, why are they doing it? Why are they not doing this in Java or in C++ or something like that? And that completely stopped. And students were just as happy about the class as they were before, even though we weren't being so unfriendly to them. Professional programmers, when you're dealing with professional programmers, we very quickly get to the point where there are examples that are not easily possible, even using the functional features of Java or C#, I guess. So I tell them I tell them ahead of time, we're using these functional languages to do functional programming because there's just a lot of things that you still cannot do with the functional features in Java and C#, but I will show them to you, and pretty soon those examples show up. So I'm going to mark that. So Dimitri, I hope that answers your question. I'm going to mark that one. Otherwise, you're just going to need to come back. Camilo asks, not a proper doubt on the subject, but the material of your teaching of design recipes in OCaml Haskell is published anywhere? No. The only material that I've published is on the teaching languages that we've developed. And so in my experience using OCaml and Haskell, I guess some of it is published. If you look on my website, there's probably some old classes that have used it, but certainly it's never something that we bothered publishing. It's just been very consistent experience that it works better using the teaching languages even for professional programs. This is the question there. Camilo? Okay, so I'm going to mark that one as answered. And Enzo asks, let me say that one, has anyone done more or less scientific studies on how the experience with a learning language generalizes to real world language? No, I don't think so. All I can say, so I think the flat out answer for that is no. All I can say is that, so year in, year out, the company that I'm CEO of, we do commercial projects using functional programming. Most of the people who work for me are my former students, so they apply these methods on a day-to-day basis, so we evaluate continually how well that works in the real world, and it tends to hold up pretty well. So I'm going to mark that one. Leonard says, programming usually does not only require to implement something in a language, but also first coming up with a high-level algorithmic idea requiring creativity. That's a great question. So let me try to tease that apart, right? I'm going to focus first on creativity, right? Of course, the design recipes don't tell you what problem to solve, right? And they also don't generally tell you, oh, you're going to need to write a function for that. Design recipes kind of start at the point where you've determined, this is what I want to compute, or this is what I want to do. And therefore, I have to write a function that does this and that. And then the design recipes guide you in actually writing that function or writing that program that does it. Now, superficially, that might seem that it's trying to take the creativity out of programming, right? Because again, right? So in practice, I think quite the opposite happens. So if you look at people who are really, whose main job is to be creative, whether that be choreographers or writers or something like that, they all emphasize kind of the hard work and systematic work on something. What the design recipes do is they ease doing the boring parts of programming. They make that substantially easier because you don't have to waste so much brain real estate on them. You just do things mechanically. And that kind of so my experience has been that it kind of frees up your mind to think about the creative aspects. So I think this is a tool to help creativity rather than impede it. Lena also said, coming up with a high-level algorithmic idea, and I'm not sure I'm reading this right, but in my experience, when we develop a piece of software, even a large piece of software, the central ideas that are behind that piece of software are generally not algorithmic ideas, but they have to do with problem domain. And it's pretty rare that we actually have to develop an algorithm, a novel algorithm to deal with a certain customer problem. So that's why. So arguably, design recipes don't help you develop, don't help you develop arbitrary kinds of algorithms, right? Because lots of algorithms, they pretty much have some brilliant idea behind them. I remember my former boss once talked to Tony Hoare, and he said, "How did you come up with Quicksort?" Right? And Tony Hoare said, "Well, it was the second idea I had after Bubble Sort," but he couldn't explain how he got that idea. So lots of algorithms have an idea where I can't explain how that idea came about. But even with those, you can often break it down, and that's also something that we can talk about more later. So I hope in this format, I'm just going to mark that as answer, Lena, but that doesn't mean that you can't come back later to something like that. So, and Feng Min asked how much semantics and even formal semantics you do in the FP course. Do students find them helpful? Again, here's, let me turn off, might have heard my phone ring a little bit. I thought I'd turn it off. So in the university course, we did quite a bit in the sense that we developed, so there's actually a section on the lambda calculus, and there's also a section on the SECD machine there. And this is those stuff that replaced earlier material where we wrote like a straightforward meta-circular interpreter, for example, that we never got to work. Strangely enough, the lambda calculus, maybe if taught in a certain way, is something, and the lambda calculus in the SECD machine, we found extremely helpful educational tools that work well with a wide variety of students. So again, your mileage might vary, but we were very surprised about how well that works consistently with our students. Feng Min, does that answer your question? Okay, good. Student asks, how would learning functional programming benefit me? Okay, good. I'm not sure how to answer. Considering that they have taken other programming courses, most of them will probably doing more routine web programming rather than functional programming. Well, I think my answer to that is most. Let me think about a little bit how to answer that one. So first of all, how would learning functional programming benefit you? I'm again going to have to qualify in saying that, I mean, of course, if you're later programming in functional languages, but that point is kind of moot, right? But how would, I guess the question is, how would learning a functional programming benefit me, even if I then have to go and program a bunch of JavaScript later in an imperative way, right? And the answer to that is really that the approach that we've developed over the years is systematic. So it really enables you to construct the program given a problem. And that might seem kind of an obvious aspect of learning how to program if it weren't the case that lots of people fail at programming, right? I don't know how many of you have dealt with professionally developed software, but lots of it is just awful, and it works. A lot of the time, it doesn't work. It's very restricted. It has lots of special cases. It's completely incomprehensible because it wasn't developed in a systematic way. It very fundamentally fails at satisfying its requirements, right? And so if the alternative is, well, you could just go to a web programming boot camp somewhere and learn programming in JavaScript directly, my answer is you're probably not going to be a very good JavaScript programmer as a result of that. And you might not be able to construct programs successfully at all, even though you've gone to a boot camp specifically about the subject that you later want to work in. Does that make sense? I really have to say these questions have really become very rare for me in the last 5 years. They were very common before that, but most of the people I deal with, professional programmers, beginners, have really have caught on to the fact that functional programming is beneficial to them. So I don't really have to answer it that often anymore. I have to look at my watch. We have lots of time. Any other questions? Here's in the chat. So Camilo asked if it's possible to see how to apply the didactic approach to OCaml. And if I tell you more about the didactic approach, I think that'll be very obvious how to do that. I'd be happy to show you, though, how we transition. So very often what I do in in professional training is people rarely come and say, we want a general class in functional programming, but they rather really would like professional training in F# or in Haskell or in OCaml or something like that. And the way that we do that is we use the teaching language the first 2 days. Usually they only have 3 days, and transition to their programming language of choice on the 3rd day, where we have to then explain how to translate the concepts that they've learned about in the first 2 days to their programming language of choice. I think that'll be obvious, but we can specifically talk about that later in the tutorial. How do you assess your, here's a great question, right, by Xin Cheng. If students' compliments or their excitements are not good measures of how successful a course is, how do you assess your course? And we've actually published papers on that. So if you Google my name, go to my homepage, you'll find 1 or 2 publications on that. So the main thing that we did to gauge how well students were doing is we really had a very close look at the final exams. And so there were different problems on the final exam on different aspects of the course, and we graded each of those problems individually. We did analysis of each problem individually, and then if one particular question, lots of students did poorly, we would try to do something else the year after, and ask a similar exam question and see if students got better. I can tell you, with some of the things that we tried, students never got better. And then we ditched that and tried something else. There's also lots of other things that we did. In particular, I mentioned that we would just have lots of sort of organizational aspects of the class at the university level where we would closely monitor how well students were doing. Because, of course, by the time students have reached the final exam, it's too late to rectify any mistakes you've made during the class. And usually, if you look over students' shoulders, it's a pretty eye-opening experience, and you get lots of great feedback by just sort of walking in and looking at what students are doing. So, but the main sort of empirical means that we did for evaluating a class was look at the final exams, and there's publications on that. I should mention that this is not a question that you asked, but inevitably someone will ask. When we present this to sort of non-FP people or at the university level, people would say, well, how do you know your approach is working? We want to see, say, evaluations. But I don't think anybody's ever used an evaluation to actually make a decision on the teaching approach. That's very rare. So, yes. So Feng Min says, wait, let me check that one. Mark has answered. Okay. So here's a comment, Feng Min. Programming course is really not about teaching a specific language, but about language models, structures, features, and how you use them. Unfortunately, a lot of courses failed. That is true, right? And so, of course, we want to teach stuff that goes beyond the programming language that we use. So there's two answers to that. So first of all, I mean, that's one reason why we develop those teaching languages, because they are completely aligned with the concepts. Unlike, the functional programming languages that everybody else is using. The other answer is, of course, that you absolutely, sometimes the question comes up is, should we use programming at all? Should we teach programming at all when we teach those concepts? Is that an appropriate thing to teach? And the answer is yes, because programming languages provide a great means for practice, right? And you need I talked about this earlier in the introduction. Is you need directed practice to get good at something. And if you let me tell you about this, you'll also find out that I guess one thing that I didn't mention in the introduction is, but I'm going to mention it now, is that we don't generally explain in the course, we don't generally explain concepts directly, but we rather have students program to those concepts first before we even, say, oh, there's a concept here. That probably doesn't make sense yet, but it might make sense later when I explain some more stuff. So Fengmin says FPs relatively requires more on the ideas, but not the language itself. Yeah, that's true. It's definitely true. So that's why, functional programming languages are a good start for thinking about how to teach. Right. Okay. Any other Q&A? So I just have to switch back and forth. Yes. So Enzo says, cognition, seems to suggest, sadly for me, that it is exceedingly hard to come up with a programming environment suitable for students, end user programmers, and engineers. That's true. I think you shouldn't try. I think you should have different programming environments depending on your target group. So Dr. Racket, I think, I hope nobody hears me here. Dr. Racket is not a very good programming environment for professional programmers. It's a pretty good one for beginners. It's not a good one for professional programmers. And just try to cater to the group that you're aiming at. It's still exceedingly difficult, right? Even to make a good programming environment for any given, homogeneous target group is still exceedingly difficult. And this is true for all the other aspects of teaching as well. And the only thing that I know how to do this is really try something, see how your students are coping with it, and then either it's fine or you try something else. Let me try to be, just so that we can switch tracks a little bit, be very concrete here. Let me share a screen here. So takes a moment to find the right window. Where is it? A moment. Except this is not. So here is, hopefully, if it shows up. Here's Dr. Racket. Make the font a little bit larger. So I'll give you a good example. Okay, hopefully you can read this. Let me make it even larger. So hopefully you can read this. So for example, one thing in the development of program by design was, when it started in 2001, testing, automatic testing was not a big thing yet. That's hard to imagine today, but back then we would often test our software manually. And when it became a big thing, we were all thinking about how we are going to integrate that into our teaching languages, right? And if you look at the way it was, I don't know when that was, around 2005, 6, 7, or something like that. We thought nobody likes to write tests. So how are we going to motivate students to write tests? And the answer was, we will provide sort of a graphical way to write tests in Dr. Racket. And it no longer exists for good reasons, but the idea was you would get like a little form. You could push a button and a form would show up. You could write like an expression here. You could write like +1. It no longer exists. I don't even have a version of that, right? And then it could say, it would say expected value. You could write something like this, right? And this would appear in graphical form, and as you and then you could push a button to run your program, and it would have like these really nice looking green check marks showing up to your tests. So the idea was to make it really pleasant to write tests, right? And we were all sure, this was going to support the students writing tests, and that will work. And unfortunately, it didn't all work at all. What turned out later to work much better is just to do a straightforward, language integrated form. Just kind of gratifying if you're, a functional programmer or DSL person. So this, by the way, says 1 + 1 should equal 2. But here it's just textual, super boring, super bureaucratic. You push a button, and it says, I'm sorry, I even misspelled that. And it says, your test passed is what it says in German down there. So we thought, so it turned out that the more boring form of expressing tests is something that worked much better for the students and made more students write tests successfully. There's no way I could have explained that beforehand, before doing the experiments on that. And lots of aspects of the class were such that we tried something that we were sure was going to work, and then in the end it didn't. We had to do something else. So hopefully, mark that one. And then at some point, yeah. Okay. So maybe, now I've got Dr. Racket up, I should, I'm trying to think about how to best do that. I should actually tell you a little bit about the didactic approach and tell you how that works in practice. Is that okay? We have 20 minutes before the break. Okay, so I see a couple of thumbs up, just to give you an idea of how that works in practice. So let me, again, to make it, if you really want to do that from the beginning, I encourage you to look at How to Design Programs, or if you speak German, to look at the Dein Programm book. So I'm going to jump in the middle somewhere to tell you how that works. And I'm just going to give you, the classic example, I guess, on lots of things when it comes to teaching functional programming. And the idea is, we call this section, it's called Animals on the Texas Highway. And I think the original example came from Kathy Fissler, and it was, was developed at a time when the PLT group was still based in Texas, right? And the idea is this: you start out by saying, well, there are armadillos, right? Armadillos on the Texas highway, right? And the way that you start is you make something. I'm just going to call that data analysis. Let me go back, right? Design recipe says you do something called a purpose statement. I should really number those things, right? Then you do data analysis, and then you're going to do something that I'm going to call the template here. Terminology varies a little bit with the How to Design Programs material, but the idea is that there's a certain number of steps after. I'm sorry, I should really do it this way. There's a signature, and there's a bunch of tests, and there's a template, and there's the function definition. So that's kind of a reasonable way. So the first idea with a design recipe is that you write a function always following the same steps in the same order. Okay. That's the first idea of the design recipes. And again, the exact sequence varies a little bit. You might also come up with your own, but the important thing is that we make everybody follow that same sequence of steps all the time for every single program, and that we also try to follow it ourselves. And I'm probably, having done that many times, I'm probably going to jump ahead of myself a couple of times, and then you can remind me. So the idea is we're going to simulate animals on the Texas highway. In particular, we're going to simulate running over animals, and we're going to simulate feeding animals. So we'll see how far we go down that road. And so, and if you look at this problem statement, you can see a couple of nouns in there. Well, the fact that they're on the highway is probably not as important right now, but what is important is this idea of what is an animal. And we're going to restrict ourselves in the beginning to just armadillos, right? And in a problem statement, the idea is this. Somebody will have written on a problem statement, right? An armadillo, might say armadillo has a certain weight and is dead or alive. And what we try to do is we try to get students to describe their data using a small set of wordings, if you will, a small set of phrases that they might use. In this case, you might make students sensitive to the fact that this sentence consists the word has a. That's already a strong hint as to what kind of data they're dealing with. I generally encourage students to look for a formulation where it either says an armadillo consists of or it has certain properties. So it has the following properties, something like that. So this is the stylized version, if you will. So this is the first part of the data analysis. So we have a problem statement. In the problem is apparent certain kinds of data, and we first write down a description of that data, a data description, right? And then we try to bring that data description into a certain form using certain phrases. And one of those phrases is, let me again mark that off, really impart on you how bureaucratic that is. Here is one of those phrases. Right, one of very few phrases that you might use. And then we might say it has a certain weight and it is dead or alive, right? Well, let me, for a change, really make the most bureaucratic version of that so you get an impression. Now, when you see that phrase has the following properties, this is an indication that you're dealing with something called compound data. You'll think, oh, this is super boring. Yeah, it is super boring. I can tell you, however, that compound data tends to be one of the more difficult subjects in class for students for reasons that I don't understand. So it's worthwhile spending some time on it. And also professional programmers tend to get it wrong a lot of the time. Okay, so first we do a data definition or a data description, in that we describe the data that occurs in the problem statement, and we try to use certain pre-canned phrases to describe it, and that will give us a hint as to what kind of data we're dealing with, right? Sometimes that description will give rise to new kinds of data. So, for example, we might say something. We're going to have to talk about what weight is, right? So we might start by saying, weight is just a number. Okay, that's fine. But here's this other thing, right? So this property, unfortunately, there's no good English word for it. We're just going to call it its liveness, right? So the armadillo's liveness is whether it's dead or alive, and we might pull that into its own data description. So we might say aliveness. And here's a different phrase, and this phrase is one of the following. That's another phrase. And there's only a handful of these phrases. A couple, 3, 4 different phrases apart from the primitive data that you might look for, right? And so it might be dead or it might be alive. You could also motivate that by saying, it has the following properties: it has weight and liveness. So there's certain didactic approaches that stress the use of the word and, right? As and then stress the use of the word or here. Whatever you do, it's probably going to work if you use it consistently. Now, the next idea is that every data description gets translated directly into a piece of code, as directly as possible. And the idea is to make that super boring. And so in these particular teaching languages, the way that we do it is when it's something like this, so this is something that's called a case distinction. So the phrase here means case analysis or distinction. And so we're going to have to find some way to represent just dead or alive. And the way that we do that in these teaching languages, we just use strings, right? Your programming language of choice might do that differently, but here it's something that people already know. And what we do here is we translate the data definition into a piece of code. And since dead and alive are strings that already exist, we create what's called a signature. And the signature just describes certain kind of data, right? There should be a signature to go with each data description. So in this case, here's a signature. Again, I'm jumping right in the middle. Of course, there'd be lots of material introducing this particular form, but and you can see here that indeed this is a descendant of Scheme or the Lisp family of languages. So what that says is, if you read it, it says, well, liveness is a signature that says it's one of the following. It's either dead or alive, and you can see the correspondence between this wording up here and the form in the programming language. So the idea is to create a correspondence between your teaching concepts and the elements of your programming language. Okay, so far? Please ask questions or interrupt me if anything is being unclear. Okay, so, and the idea is, okay, so if we have this particular thing, here we have something that's even more restricted, an enumeration. I'm sorry. Alternatively, you could also write enum here. That also works. Works, yeah. So up here, we said we're dealing with compound data. And every programming language has different ways of, has a different way of expressing compound data. In the teaching languages, we use something called a record. And so I'm just going to make that short. I'm just not going to type out armadillo. Every time I'm just going to call that dillo here. I'm just going to type it out first, and then I'll explain it. So this is how that works. And we're going to say dillo liveness is okay. So what is this? I'm just going to explain the concepts here. This thing here is called the signature. So it's just called dillo that I can use as a signature from now on. This is a constructor, and this is, depending on where you're coming from, a getter function or something like a selector. So let me show you how to deal with this. You can. This is the Dr. Racket programming environment. You can push the start button up there, and then you get into a REPL, which is an interactive shell. And I can, for example, say make dillo, and I can make an armadillo that is like this, make dillo 12 alive. And of course, I can create examples also in the source code. I can make a dillo 1, make dillo 12 alive. What we ask students to do, and hopefully, you can see now that there's this direct correspondence between the data definition here, okay, and this record form here. Record form is fairly complicated, but still you can see, okay, it is an armadillo. A dillo is this thing. It has a constructor called megdillo, and then for each thing that shows up here, we have something show up down here, right? So the weight corresponds to the dillo weight selector, and the liveness corresponds to the dillo liveness selector. And now when I teach, it becomes super bureaucratic in the sense that I ask people to count the number of components that their compound data has. So, in this case, I'm going to say, how many components does an armadillo have, or how many properties does it have? And I really want to ask students to hold up like 2 fingers or hide them and say, everybody at once, 2. You would be surprised how often students get that wrong. So it's very, very pedantic here where we say, make sure that the number of components in your data description matches the number of components in your record definition. And the same thing down here, when we have that case distinction, make sure that in your data definition, it has, when it has 4 cases there, make sure that your signature definition also lists 4 cases, right? So it gets very, very detailed and pedantic, right? And when we do this, right, we have an example object that represents something in our domain. We ask students to provide a comment that explains the relationship between the data and the information represented by it. So this is an armadillo. It's alive, and it weighs, for example, 12 kilograms. That immediately exposes maybe a potential weakness in the model that we have here, is that it's unclear what that 12 means without the comment that goes with it, right? We might make another armadillo that sits below, 10 in bed. So, armadillo. And so far? So, whoops, just saying this. Any questions so far? So this is the data analysis. The idea is basically that in order to structure your data, let me just data analysis. Just for structuring data, we will use what's called compound data, right? Several things become one, right? And then there's case distinctions, which kind of sounds funny in the English language. We generally call that mixed data, where as part of one data type or one data signature, different kinds of data can show up. And we will later see that there's also something called a self-reference. So these 3 things are the primary means for structuring your domain data, right? And they're pretty easy to remember. This is the thing with the and, this is the thing with the or, and the self-reference is sort of an emergent phenomenon. And so we will ask students, to look at their problem statement, look at a particular entity that shows up, in this case, the armadillo, right? We will ask them to write down a description of that entity or that piece of data that they're looking at, and then see which of the phrases that I've used to describe data, where it says either consists of, has the following properties, is one of the following, which of those phrases applies. And usually it's only one of those phrases that applies, and that's not usually a point of contention. And then there is a specific template. There's a specific design recipe that provides a template for the code that then needs to be written. And the code kind of derives mechanically from the data description. So it's very bureaucratic. But because everything is explicit, right? All these design recipes are explicitly listed. There are in the book, or they're in the online help. It's something that you can always refer to in class, right? When people are having trouble, you can go back and say, well, look at the design recipe. It tells you, if you don't know what kind of data it is, it tells you to look for one of those phrases here and find the phrase that matches your data. Or when people are having trouble writing the code that corresponds to your data definition, you ask them, well, is it compound data? Is your case analysis going on? And then go to the appropriate design recipe where they will find a template for the code that they need to write. And that approach is very, very successful, getting students of all ilk to then translate that into working code. And I will also mention, and somebody asked earlier, right, what is the motivation for doing this, even if you're ending up later as a web programmer doing JavaScript? This is something that, even though it seems very simple, even in professional software, for people who've not been trained that way, it goes wrong surprisingly often. So I can't stress that point enough, right? That we like to propagate the myth that lots of people can program and lots of software gets written, but a lot of it is just terrible and wrong. And in particular, what often ends up being terrible and wrong is the data models, right? And of course, these ideas of having compound data, case distinctions, and self-reference, these can be translated just about into any language, but usually using different sets of differently coupled concepts. So that's something, for example, that would be relevant once somebody transitions to OCaml or Haskell, or one of those languages that have algebraic data types, for example, which use a combination of these things. Okay, let me maybe before we break a little bit, let me do one function on this. We said we want to simulate an armadillo getting run over, right? And so we want to write a function that does this: run over an armadillo. Okay? And you mentioned that you might remember that up there it said the first thing you do, that's the purpose statement. And the next thing that we're going to write is the signature. And the signature looks like this. We're just going to write a function that is called run over Dillo. And that function accepts a Dillo as an argument and produces a Dillo as an output. Okay. This, by the way, is also an example that I use often to explain how functional programming differs from imperative or object-oriented programming, right? Isn't that it's not a function that is like a void return type or something like that. Okay, is that right? So it looks like a type signature. It's not, by the way. It's not a type signature. Next, it said write a bunch of tests, right? We've done the data analysis, write a bunch of tests, right? And it might look like this. So we write run over Dillo. We could just run over Dillo 1, and it should produce a Dillo object that weighs 12 kilograms, but it's dead, right? And if we run over, that's very informative, Dillo 2, well, if we run over a dead Dillo, it just remains the same. It's sad as it is, right? So just need to drink this up. So we provide a bunch of tests. There are the tests. And what's important here is, at least specifically in a classroom setting, right? Students, at least in the beginning, they like to skip over some of those steps, right? As you'll later find out, that, for example, the signatures are optional. And of course, the tests are optional. But we really insist on not just doing those steps and doing all of the steps, but doing the steps in that order. And for example, in class at the university level, we would refuse to help students with a step if they haven't done all the steps that are supposed to be before that one, right? So it's really, again, very bureaucratic, but it's something that really works. The next thing that happens, and this is something that I found hard to explain how that goes, or that I found hard to learn from just looking at the book. We do something called, well, actually, in our approach, we first do something, I'm going to call it the skeleton. It just says, well, if you have a function that we already know the name of the function, and we also know the signature. And so what we can do is we can write a very rudimentary, some very rudimentary elements of that function definition. So I'm going to write run over Dillo. We already know. So in order to define a function, we use define. Run over Dillo is taken from here. Whenever we write a function, we write lambda. Okay? And we have to think up a name for that argument, but we know there's only one argument. We're just going to call that Dillo also. And I make 3 dots here. And the important thing is, right, in class, actually write 3 dots. I can't stress how important that is, right? You might, from reading the book, you might just think, oh, I'm going to then, it just comes later what I'm going to fill in there. But the important thing is to write it out. In the beginning, I will often even do this, that I will let this remain in the code and just comment it out. You can comment something out by saying # semicolon and then copy it. So to evolve it into later steps, the next step is what's called a template, right? Just to show you the succession of steps that goes on. Now, don't worry, we're not going to need long. Now, the template says you use the data definition, the data analysis that you've done, to put a couple of pre-made elements, if you will, a couple of elements that you are likely going to need into your function body, right? In this case, we're dealing with compound data in, right? We have compound data as input. And whenever we have compound data as input, we need to look at the components. And we look at the components by just writing down the selector expression. Depending on the programming language, there might be different syntax here, but here you write it down by saying liveness, like this, right? And the important thing is, right, this is not a complete function. These are just things that you're going to need. So you write this without thinking. That is the important aspect of this, right? Just from the shape of the data, any function that has this signature, where it says dillo, arrow, dillo up here, you would write this particular template. Is that clear? Right? Always the same. You do it without thinking. And we really stress that with the students. Write it down. And you would not believe if you don't have that, or if people forget about, students tend to forget about this, and they think that they come to the conclusion that they do need to think about this. If people start thinking about it, they will often stall at some point or other during this process. So it's really important to emphasize the mechanical, bureaucratic aspect of this, because otherwise lots of students will get stuck, right? Really explicitly, do not think about the problem at hand at all. Just fill out the template. Here, there's actually another template, which says, this is template number 1, right? And here's template number 2, which says run over Dillo. I don't usually write it out this way, but you see it. It's not just that compound data goes in, but compound data comes out, right? And in order, if you're going to have new compound data, then you need to call the constructor. There's no other way of making new compound data. So you write make below, and you write this. This is the template number 2. And this is like a form, right? You need to fill out these two things, right? What is the weight of the armadillo? And is it dead or alive? What is its liveness afterwards? And only after you've written down those templates, and you've actually written them down, not just in your mind, but you've written them down in your program, and preferably documented them for your TAs or whoever's going to grade your assignment. And only once you've done that, you do another version where you fill out the form where you say, well, I've got a first question I need to answer. It's what weight does the dillo have? And the answer is it has the same weight as before, right? Running over for some reason doesn't diminish the weight. So I copy it. It's already there, right? The important thing is it's already in the template. And so the important thing is I'm going to copy this from down here to here. And the other question is, well, what is its liveness? Well, after we've run over the armadillo, it's always dead here. So at this point, you might have noticed we have not used the liveness of the armadillo before. And this is where we instruct students to, well, if you haven't used one of the attributes of your compound data, then you should probably think for just 1 second whether that's justified. In this case, the student might go, oh, with the armadillo, it does not matter whether it was dead or alive before. The main thing about running over an armadillo is that it's dead after. So it's okay to leave out that call to the selector, right? But the important thing is you've typed something in that you end up not using in the final program. And hopefully that gives you a vague idea of how bureaucratic this approach is. Any questions so far? Okay. So my suggestion is this. We're supposed to have a break now. I've run 5 minutes over. I'm just going to go to the bathroom for a minute. I'll be back in about 5 minutes, but we'll resume sort of the official part of the tutorial in a half hour, right? At something 35. but I'll be here to chat. Okay. And I can take a break. Wait. That will stop the live. And it says there's a take a break button. So if you're, I'm just, take a break. So welcome back. If you're already back, just going to wait, I guess, 1 or 2 minutes longer for everybody who wants to return. But if you have a question already, then be sure to ask. I'm going to bring that up on the screen already. Okay, lots of people are back. Maybe we'll give that 1 extra minute. All right, I guess it's time to start again. Does anybody have a question or a comment so far? I'll just talk a little bit about the things that we've seen, and maybe you can jump right in then. Let me maybe explain to you a couple of the things that might not seem so interesting in passing, but that actually took a lot of time to come up with. So maybe a little bit of history. So one of the great things about Dr. Racket is not just that, it started out as a development environment for beginners, but also that the Racket language is kind of a toolbox for building languages. So you can just build a language and ship it as a library, as a package, essentially, to load into Dr. Racket. And when we started developing our teaching languages, which are slightly distinct from the how to design programs ones, we were able to just ship that as a package for the students to install. And in particular, in the beginning, we just shipped a new version every week. And this way we were able to make incremental improvements as we saw how the students were coping with that. So maybe one innocuous aspect is the fact that you can write tests right in the same file as the code itself, right? Here's these check expect forms. And that might not seem very exciting, but in almost any language to use any of the test frameworks that exist there, you almost always have to write the test in a separate file. You have to deal with the module system, with the build system, other aspects. And so here it's really important that the tests are really part of the same file. And also that you can write them in a place that corresponds to the order of the steps in the design recipe. So the idea really with the design recipe is each of those steps, you write them down, you write something down in the same order as those steps. And also, if you're in a classroom setting, is that every step produces output, and that output can then be graded. And so you can make sure that people really get credit for following the design recipe. Another aspect is this thing up here is the signature. And if you look at how to design programs, the signature, I think there is called a contract. There's only a comment. Even though we've lately made great progress also having these signatures in the how to design programs languages. And mainly, so first of all, maybe you can believe already that these signatures are extremely useful to get students to think about, oh, I'm going to write a function to solve a problem, what data goes in, what data goes out. So that's very useful. Our experience here in Germany was that when it's only a comment, and students are very aware of the fact that it's only a comment, they would just be very sloppy about writing down these contracts/signatures. And so we wanted a way to actually write them as a piece of the code, and this is the notation that came out. It does look a little bit like a type annotation, but it really isn't. Let me maybe see here that I could make something that could be like a type error. Just swap those two arguments, and you can see that, well, you get a window here. Unfortunately, with maybe I need to make the letters a little bit smaller temporarily. So here is a check failure that says, oh, the actual value differs from the expected value. So that's just your ordinary report of a test failure. And you can also see here a signature violation, which says, well, I got dead here, but I violated this signature. And you can see that this is a clickable link, and you can see which signature specifically was violated. Now, these signatures are not type checked at compile time, but only at runtime. And they don't, even when there is a signature violation, it doesn't actually stop the program. The program goes on. It just makes a note and logs it, and we'll display it later. And the reason for that is that one of the things that makes a programming environment and a programming language good for teaching is to give good feedback. And in this case, the feedback is, well, you violated some signature, and here's the actual value that violated the signature. And this is the output that you will often not get from a type system. And I'm sure I'm sure those of you who've taught with a statically typed language, you know that it's sometimes difficult to explain what a type error message means to students, right? And here really it's just that, oh, you got this value dead by doing this, by evaluating this form. So this is also a clickable link, and you violated the signature, and that tends to get students on the path to actually fixing the problem. Okay. So the signature concept is something is an example of something that is that was really developed specifically for the teaching languages. In this form, I've seen variations of that in Clojure, but the idea in this form I haven't really seen anywhere else. Any questions so far? Or comments, for that matter. All right. Now, I think I'm just going to continue writing this program and then show you some of the important aspects of that. So I hope you all got this point of doing first what I call the skeleton. So just do this thing where you just write define lambda, and you just write 3 dots where the body is. Actually write that down. That's important. And doing the template, that's almost the most important part of the design recipes for functions, is that you always use the shape of the data to then derive elements of your program that will later be in your program, and you also write them down. So again, very important to have students write it down. Often students, after they've done it 2 times, they will think they can do that in their heads, but they can't often enough. And there's this funny situation where you have to remind students to just follow the design recipe and write that down, and where they're sure they could do it in their heads, and they're running into some problem, but still somebody else has to tell them to do that. Okay, so far? Good. So let's imagine we'll defer the feeding for a little bit later, but let's imagine that, well, I mean, this whole thing started with saying animals on the Texas highway, right? Now, of course, there's not just armadillos on the Texas highway. There might also be, I don't know, a parrot, right? And a parrot has the following properties. So a parrot always has a sentence because these are all speaking parrots, and it also has some weight there, right? We'll just do it that way. And again, you know, when you see this wording here has the following properties, then we can, of course, that might result from some refinement process over the wording, but once you've reached that, after a while, students will just naturally pick the right kind of wording. So if you have this, a parrot has the following properties, you know you're dealing with compound data, and therefore inevitably a record definition must follow that corresponds in shape with the data definition here. So you might write define record, parrot, right? Make parrot. And we have the parrot sentence, that's going to be a string, and parrot weight as a number. And by the way, what you can also do is you can write down signatures for the functions that are defined by the record definition. So you could, for example, write make parrot, and in goes a string and a number and a parrot. Or you could also write down signatures for the selectors. So you would write something like this, parrot sentence, parrot string, extra parentheses, and the parrot weight, which goes from parrot to number, right? And I very distinctly remembered when we introduced this, because students sometimes in the beginning have trouble with this notion of selector function, especially if they have some background in Java, where in order to access a field in a class, they can just write dot weight or dot sentence or dot liveness or something like that, right? And they're kind of confused by the fact that it's just a regular function doing it here. But it gets much easier if they know the signatures of those functions. And so I remember one of the iterations in the early language versions is that we put in this ability to write down the signature of the record functions, which helps students a lot. Now, you will notice that now the signature information about the record is now there in triplicate, right? So it says here, parrot sentence, that's a string. Of course, make parrot accepts an argument for each field. And so there's this string is the same string, it's the same thing as this. It's the same thing as this, it's the same thing as this. So for every field, there's now 3 places where it says what that signature is. So it's highly redundant and super bureaucratic. But I distinctly remembered when I said, oh, well, we now have that information in triplicate, I'm just going to write it down once. They said, no. So I remember in class, the students said, no, we would rather have you write it out, at least for a while longer, because it helps us deal with the records. So you could do that. So the signatures have proved a great help generally in helping students along with writing their programs. So we have this, right? Again, we're going to make a couple of examples. So we have parrot number 1, which is a parrot that says, this is the hello parrot, weighs, how much does a parrot weigh? A kilogram, maybe. And again, there should really be a comment that explains the relationship between information and data, right? And so here it says, parrot that says hello and weighs 1 kilogram, and maybe there's another parrot, goodbye, that weighs 2 kilograms. 2 kilogram parrot says goodbye. So always with compound data, it's always a good idea to have examples along with the data definition. Of course, that's also part of that systematic approach. All right, now we're just going to imagine that we're just going to go through the same thing, right? So we get into, you imagine you live in Texas, right? And you know, in the first instance, you get into your big truck, you get on the highway with the intention of running over an armadillo. And now there's parrots too, so we're just going to run over a parrot. So I'm sorry. So we have, we need, and you might have noticed me getting ahead of myself, right? I really shouldn't do that. So we, again, need a purpose statement. We need a signature declaration. It says, oh, our function is going to be called run over parrot. It has signature, parrot in, parrot out. And you should, again, make sure, typically using the examples. So when we have run over parrot, then well, what's going to happen to the parrot? It's going to go silent, right? As you run it over, it goes really quiet. Otherwise, some wait as before. And if we have parrot 2, of course, it's also silent. Okay. Now we kind of go through the same steps, right? We go, and here I'm going to shorten that process a little bit, but show you. So here is the skeleton. And I mean, you notice it's kind of the same program as with the armadillos, but we're really trying to get to a different point. So in the template, right, it says parrot sentence, parrot, and it goes parrot weight of parrot. So those are the things that we might be interested in about a parrot. And the body, because it's not just parrot in, it's also parrot out, needs to consist of a call to make parrot. And once again, we can say, well, here in this case, well, what does a parrot say after it's been run over? It says nothing. So we put the empty string there. We put the weight in the second slot. We have this left over, but as with the armadillos, it does not matter if what sentence a parrot said before, afterwards, it's silent. So again, I can push that run button up there, and it will tell us, oh, it's getting better. It says all 4 tests passed. That has turned out to be perfectly enough feedback for the students. Actually, let me show you one other minor aspect which is built in, which is that if I comment out those tests, you can see that some expressions are marked, and these expressions are this is a coverage annotation. So it shows students in not so pleasant colors, oh, you forgot to run something, and you should probably write more tests to get that coverage. And so that's worked pretty well in practice. Okay, so far? Any questions? Make sure to jump in. Now, you might have noticed it said animals on the Texas highway, right? We might not know whether the next animal that we want to run over is a parrot or is an armadillo. So what really happens is that really we have this concept of an animal. I'm going to run over the next animal that I encounter on the Texas highway. And then you might say something like this, right? An animal is, and you might say it is an armadillo, or is a parrot. And again, you could either use the word or here, or you could say one of the following. And this gives you an indication that we're dealing with mixed data. Okay. So wait a second. So we don't need any new data, right? So we already have armadillo objects and we have parrot objects. All that we need now is this notion that there might be places in the program where both armadillos and parrots pass through. And to that end, just as we did before, we just need a signature. We don't need something akin to a record definition. We just need a signature that says, well, an animal, that's a signature, and it's mixed together from the armadillo and the parrots. Okay. And again, in class, we go through the same motions where we say, well, how many different kinds of animals are there? 2. How many cases do you have in your mixed signature? 2. Do those 2 things match up? They do match up. I think you get the idea there, right? And here, for example, is an important difference with the typical functional statically typed languages such as OCaml or Haskell, right? In Haskell, you would write this differently. You would write data animal is equal to what did I say? Below it was like weight and liveness or something, or parrot string and weight, something along those lines, where the concepts of the concepts for mixed data and compound data, they are both conflated in one single programming language construct, right? And we all know why that is, right? Algebraic data types are great, but here the problem really is in order to mix up the parrots and the armadillos, we have to throw away the old data type definitions and make up new ones. So we have to go back and change the program that we've already made. And so that really is well, it's unfortunate from a software engineering standpoint, but it's also unfortunate from a teaching standpoint, because intuitively you go in there and you go, well, we already have parrots, we already have armadillos. Why do we now need to change it so that they're both defined in the same place, right? And that's something that you can appropriately explain once people have grasped the concepts of mixed data and compound data separately. And then you can say, well, there are some languages where these concepts are entangled. And of course, there are languages like typical object-oriented language where you would encode them in a different way. But the important part is that you have understood the concepts up to that point. Okay. So, and with this concept of mixed data, again, the same idea is, applies when we're writing a function. So we could now say run over an animal. So here is the purpose statement, which is write function. We'll just call it run over animal. We'll write it as the signature. And the idea is, for example, when we run over Dillo1, we kind of expect, we could just write the same expression, but we could just say, well, running over the animal Dillo1 should be the same as calling run over Dillo on it, right? And same thing as when I call this parrot1 run over, it should be the same thing as calling run over parrot. So that's one way to make the test cases here. Okay, so again, we go through the same steps. So we write the skeleton. Who knows what's going to happen here? And now the idea is that when we have mixed data, what we need is we need some kind of branching construct that corresponds to the different cases in our case analysis, right? So we need a branching construct corresponding to case analysis. And in the teaching languages, that construct happens to be called cont. And the important thing is, so this is one branch per case. And again, it might seem trivial as you're teaching, right? That you say, well, your branching construct, it should have as many cases, it should have as many branches as there are cases. So, but watch yourself when you program, you often optimize that, especially if you have several nested conditionals and so on. This is something that you should not do when teaching. You should really stick to that rule that these numbers correspond, right? The data definition says how many cases. The signature definition says how many cases. And here the function operating on this data also says how many cases. Now, what we need here is we essentially need a condition here that tests whether this is an armadillo or condition armadillo. Condition, and what was the other thing? The other thing was right. We need a condition that tests the animal object on whether it's an armadillo or a parrot. Right. And at this point in class, right, where we go back is, well, we don't have that, right? We have compound data. We know how to construct it. We know how to take it apart, but we don't know how to distinguish from other parts, other pieces of data. So we could go in and what we do is we augment the record definition. And so what we go is we write after the constructor, we write something called parrot question mark or parrot p. Parrot p. Well, any value goes in and a Boolean comes out that says whether that's a parrot. So it corresponds, I don't know, to instance of if you're coming from Java or something like that. The same thing in Delo. Signature. I'm going to write that out now. And so what we can do then is we can, and again, imagine I'm leaving huge gaps in the curriculum where we talk about case distinctions and how to write functions on that. So this is now about the combination of mixed data and compound data. So we write also the predicate here. And this one. And fortunately for those two cases, we've already written functions, so we can just call run over below. And here we call run over parrot. And again, right, again, imagine you're doing this in OCaml. You can't even properly factor the function that way, right? In that you write two separate functions. It does not, it's very awkward in a language like Haskell or Parrot. Not Haskell or Parrot, Haskell or OCaml. Ah, I made a mistake. Or it says record parrot. That's right, it said parrot of parrot, but it needs to say parrot of animal. There, something along those lines. Okay. So, and all tests pass, so this is good. And this is a large part this is a large part already of the data modeling aspect of the curriculum, if you will, right? So we encourage people to look at their domain, look for the nouns that occur in their domain, write data definitions for them, translate those data definitions straightforwardly into code, and then write functions that operate on them according to the problem statement. And that's something that generally works quite well and is something that a large proportion of the students in all kinds of contexts that I've been teaching this in are able to do. So I kind of feel like I'm talking to a wall right now. I need a question or a comment. I'm just going to drink until there's a question or a comment or a request to explain something. I'll just sit here for a minute or two. No question, no comment. Somebody want to raise their hand so I can ask them on stage? Oh, there's a raised hand. Hans-Georg, you have the microphone. There you are.
Okay.
Yes, thank you.
So, signature function and the mixed function, these are for mixed data types. Can you elaborate a little bit more about the signature function and what it relates to with a record? So, yeah.
Okay. Yeah, good question. Please stay here to make sure that I answer your questions appropriately. So first of all, so what signature does, signature is not a function. This introduces signature syntax. Okay? So here, for example, when you have a signature declaration for a function, the signature syntax is implicit, right? You say, well, run over animal, and the only thing that can be here is the signature syntax. But if you use it outside of a signature declaration, you have to say, I'm actually making a signature. And the reason for that is that signatures are regular values, and they are subject to the same rules as all the other values in the language. And in particular, later, we also abstract over signatures in a systematic fashion. So that's the reason why that signature word has to be there. For students, it's an easy rule of thumb, right? Is whenever you're writing a signature definition, then you have to write that magic word signature there. Also, by the way, part of, I remember distinctly that we started out by having a special form that said define signature. So it used to look, so an earlier version of this looked like this, where it said define signature animal mixed little parrot. And for some reason that I can't explain, but this consistently caused confusion, which this form here does not. So there's that.
Okay.
Okay. Now with records are kind of complicated because really you need to make something new because you're not using the existing values. So here, the thing is that define record, which is why it's called define something. So define record defines a lot of things for you, right? So among other things, it defines for you a constructor, it defines for you a predicate, it defines for you these two selector functions, and it also defines for you a signature. And that signature specifically is able to tell parrot objects apart from other kinds of objects. Does that make sense? Does that answer your question?
Yeah, thank you. Yeah.
Right. So, yeah, I guess, yeah, so I guess the record definition form really is the most complicated form that we have in the teaching languages. And I think one might legitimately complain that it's too complicated, but I can assure you that it's had predecessors that were more complicated than this one. So this is the simplest I've been able to come up to this day. Okay. But is there a particular aspect, Hans-Georg, that is mystifying to you about the defined record? I didn't spend a lot of time explaining it.
No, it's clear to me. Thank you.
Okay, good. Thanks. In particular, also maybe if you're looking at how to design programs, right? How to design programs, it's not a record, it's called a struct. So what you write there is you would write define struct parrot, and you would just write this. So it has a much more concise notation. In particular, you don't need to write out. So this automatically makes up names. Make parrot. Automatically defines names. Make parrot. Parrot sentence. And parrot weight. So whereas here you write out those names, and also that's something that our experience has been very consistently that students find it less confusing, even though it means more typing. So non-goal for all of this is to avoid typing. Right? And it used to even be called define record procedures, I think. And we even had an evil form called define records parametrically that people had to type out. Fortunately, that is long gone. Any other questions or comments? Okay. Any aspect that you're curious about how it's covered? I mean, obviously can't do all of it. I mean, there's something I could do next, but anything that anybody's curious about, or nobody's expressed any doubts so far or any differing experience. Is that still the case? You still here? Okay. I mentioned, but I hope it's pretty clear now, so that there's this data structuring taxonomy that we have, right? And the main building blocks that we have is this compound data, and it's this mixed data thing, right? You know, if you're doing this straightforwardly translates into what you might have in OCaml or in Haskell, except that in OCaml, of course, the concepts of compound data and mixed data are all part of the same programming language construct, unless you're using these funky union tags. I'm not sure how that would work out in teaching. Okay, so that is already that already lets you do a lot of things for sort of domain modeling, where people have natural language formulated problems, and you then write something like a data definition for the parrot or the armadillo or the animal or what have you. At some point, however, you realize that this is all, I think Matthias calls this fixed size data, right? So if you just have these things at your disposal, then if you just have these things at your disposal, then everything has fixed structure. There's no way to make something that has variable size. In particular, you have no way to make like a list that might sometimes have 5 elements or 10 elements or 11 elements or something like that. So in order to have variable size data, we need one more concept, and fortunately it doesn't require a new programming language construct, but that is called a self-reference. And the way that it's usually done in class, or that we've done it in the past, 10 years or something, we do this, we introduce this using lists. But I've just written a new chapter for the book trying that out, to have something that is a little bit closer to actual domain modeling before we come to lists. Now, for lists, if you know lists from your favorite programming language, fortunately, it seems all functional languages agree on what a list is. You can write something like this, right? You can say a list is one of the following. It is the empty list, or it is a cons list consisting of first element and rest list, or something like that, right? Important to explain is it's important to explain to students that this is a more or less, it's not quite arbitrary, but there are other possible data definitions that might describe sequences in some sense. But this just happens to be the sweet spot that is particularly useful and yet simple, right? And so the cool thing here is that we can. I need to select the beginner level. Let me maybe point out one aspect of this. So you can see down here, hopefully, you can't see it very well, but you can see where it is, and now I can click it up. It says language : schreibe dein Programm. And if you try out Dr. Racket, you will see that it is that there's a language menu where you can select this. What we go through in the regular course is there's not just one language. We actually have a succession of 4 languages, and I think How to Design Programming even has 5. I'm just going to look at that. So the language menu, which unfortunately doesn't go over in screen sharing, the How to Design Programming actually has 6. So I'm going to switch to a different level where it says Schreibe dein Programm Anfänger. I'm sorry I have to bother you with the German. Anfänger means beginner, right? So there's a beginner level. And in particular, the beginner level does not have lists, so we can define them ourselves. So, so the way that we deal with lists is we write our own definition rather than use the existing one. So we don't need any special syntax or anything like that. There's no magic involved. So again, we can use the means for data structuring that we've already seen many times at this point, right? There's just 2 new things. So I mean, here we could kind of see consists of, right? This so this phrase here is also an indication that we're dealing with compound data. But also here, we can see that the word list appears in the definition of the word list, right? And so this is why this is called a self-reference. Okay? And so we tell students whenever you're dealing, or your domain contains data that has variable size, that can have variable structure, inevitably some kind of self-reference is involved. And of course, that's also one of the great benefits of doing functional programming modeling, is that we have all this history and all this folklore of doing combinator models, which, for example, the people in object-oriented programming completely lack. There's also the minor problem where we need to use a trick, is how to do the empty list, since the empty list is something that has no properties. But here's something. So here's a trick that we explain to students. We just model this as a record. We just say empty list, make empty, and MDP. So we can make a record type without any fields, and we can just, since there's only one empty list, we can just, just construct that one. And now the next point, and now everything, we're not seeing anything new, and the students are not seeing anything new, but what we can now do is we can say, well, a cons list, right? If we write it out, we can say a cons list consists of the first element and the rest list. At this point, we might notice that, what is the signature of that? There's different ways of covering that. Usually what I do in the beginning is I say we'll start with lists of numbers. So anyway, so this translates straightforwardly into cons list. It has a constructor cons, has a predicate cons p, has this, and so in this case, we will need to refer to something called a list of number, and so we kind of need to tie the knot here and say, well, define the list of number is mixed together from empty list and cons list. Okay. So that's generally how we treat lists, and from there on many other data structures in class with this added element of self-reference. But this then is really all there is to it, right? Is there's nothing else. There's the primitive data types that are built in. There's the numbers, strings, Boolean values. I think that's pretty much it. And then for structuring data, we just have compound data. We have mixed data. And we have self-references, and that's it. And so it provides a very small framework for doing data modeling. And more importantly, there's a programming language that directly lets you express each one of those things. So compound data is separate from mixed data, and these are two completely separate concepts. And that means we can explain them separately, we can program them separately, and we can combine them after the fact. And that's proven. Helpful when teaching professional programmers, as opposed to when they want to learn something like F# or OCaml, as opposed to just using the same didactic approach but starting out in F# or OCaml or Haskell or any of these other languages. And then it's much easier when we transition to Haskell or OCaml or F# to then say, well, in these languages, we have this construct called an algebraic data type, and it does compound data and also does mixed data all rolled up in one. So let me try that out, make sure that, see, somebody asked about that signature thing, and here it actually says, mixed can only appear in signatures is the German language error message that you see here. So I need to write a signature form here, but then it should be okay. We can see that we're still lacking coverage. Okay. So what else should I do or explain or demo or answer? Just going to wait for another 1 or 2 minutes. So, okay, Hans-Georg is there. Yes, Hans-Georg.
Yeah. So you were saying that you have basically compound data, mixed data, and self-reference. And the
Yes.
last example, you use self-reference. So can you explain a little bit and maybe show us something about self-reference here?
Yes, absolutely. So you see here, I mean, here you can see we're using list of number. So list of number, right, is explained in terms of empty list and cons list. And cons list is explained in terms of list of numbers. So there's the self-reference. There's the exact correspondence to the appearance of the word list in its own definition, right? And
okay.
And the same way that we said that, well, if you're writing a function that accepts compound data, right? We said you always write calls to the selectors. And we said if you have a function that produces compound data, you write a call to the constructor. And if you're writing a function that accepts mixed data, you need to write a conditional, some kind of branching construct that has as many branches as there are cases in your case distinction. And similarly, if you have a self-reference, there's also something that ends up being in a program. So if we're going to write a well, let's maybe write a demo function, a demo list, first of all, right? This is, so here's a list. So here's a one element list. It just has that one element that is 5, right? I'm sure you all know this, right? That it's important to explain when you're explaining lists that it's an asymmetric construct. So if you have, I don't know, 3-element list that consists of 5, 7, and 12, then that would be, let's call it list 3, cons 5, cons 7, cons 12, and 8. So we've got that. And now let's say we're writing add up elements on a list, right? So here's the purpose statement, and we could write list sum, and we write list of number, and out comes a number, right? And the idea is that if we call list sum on list 1, well, we would like 5 to come out, and it should be 24, I think. Okay, so those are the tests. Now, most of the definition of list sum, right? Again, we do the skeleton, so we feed in a list. So here's the skeleton. Now we know, looking up, that right, a list is one of the following. It is mixed data. Of course, here the signature definition says mixed right there. So when we have mixed data, we automatically need a branching construct, and it has 2 branches because there are 2 cases in lists, right? So we have this thing where we say, is it empty, or is it a cons list, right? This is all really important. This is all stuff that you can write down without thinking, right? It comes from the templates that the students already know. And moreover, because in the second case, you're dealing with compound data, you can write down calls to the selectors, right? There's first of list and there's rest of list. Okay, you can write these things down. So this just all comes from the templates that the students already know, or that you know at this point. And now the next thing that comes is that if you have a self-reference, you always write down a recursive call. So that's what the design recipe says, is always write down a recursive call when you're dealing with self-reference. So here, the self-reference is here with the rest, and you write a recursive call. Now, depending on where you've had your intro class in programming. I remember mine, so I was being taught in Pascal a long time ago. The subject of recursion was always, people always thought it was difficult. Here it really is not difficult at all, because we're saying, without thinking, you write down a recursive call, and now you have this template here that you still need to fill out. And then we tell students, well, read out loud what you're seeing here, right? you're seeing, okay, I'm computing. So if you're here, right, we're writing a function called list sum. It accepts a list. And, we're checking whether it's an empty list. We're going to need to get to that. But if it's const list, well, we need to do something with the first element of the list. And just reading this out, it says the sum of the rest of the list. That's just literally what it says. Well, not literally, but very closely translated to English, right? What it says here. It's the sum of the rest of the list. And then we can ask students, well, if you have those two things, you have the first element of the list, and you have the sum of the rest of the list, can you then compute from those building blocks, can you compute the sum of all the elements of the list? And by and large, students then say, well, no problem, we're just going to add those two numbers, right? And so you kind of, I think somebody asked a question early on about the concepts of programming or computer science. And you'll note that we're not, that we don't explain the concept of recursion or, God forbid, fixed points or something like that, right? At this point, right? We don't explain it. We just say, well, whenever you're dealing with self-references, you put in a recursive call, and you do this without thinking, and you use that as a building block for the function that you're writing. And this is something that students can do. They don't have to get a knot in their head, in their heads, thinking about, this. Oh, what is this difficult concept with recursion? Instead, we're doing that through saying we're not explaining the concept of recursion. We're just we're just telling students how to use it, right? And I think that's a pretty significant point. Also, that depends on the level of students that you're dealing with. It makes sense to talk a little bit about what should go here. You can have a discussion amongst your students whether it even makes sense to have the sum of an empty list, but eventually, you could try putting in different numbers here, but eventually you'll end up with 0. And depending on, when I'm dealing with professional programmers, this is a good time to introduce the concept of a neutral element or an identity element, and to have people try to remember if in high school they learned about these things, right? But that really depends on what kind of students you're dealing with. But you can just try plugging in different numbers and see which ones give you passing tests, right? So that's sort of the aspect where we say, okay, self-reference is something that occurs in lists, and of course there's a large body of material devoted to lists, because it also naturally segues into higher order programming when you're dealing with all these useful higher order functions on lists that you can derive by systematic abstraction. The second part, Hans-Georg, I think from your question is then, so this explains how you're dealing with self-references that somebody else introduced, right? So the data type for the list kind of drops from the sky, and we say this is how lists are done. The next aspect, and I think that is probably more advanced, I'm not quite sure where it fits in the curriculum, but it's something I regularly do with professional programmers, is, well, how do you figure out where self-references fit in your own domain model? And the answer is kind of wherever the answer is to really actively look for places where you might conceivably put them. We have a chapter on that, but I have to admit that I don't have a lot of practical experience yet how that, or not enough anyway, to be valid to really say how well that works in practice. I don't know if that's where your question was aiming.
Yeah, but thank you very much. Also, the explanation was very good. Thank you very much.
All right. Good. What else can I do for you? So that's lists. Let me maybe go back to the beginning of the class to explain sort of a meta design recipe, if you will. So an early version of an early edition of our book was called The Force of Abstraction. And so one important aspect of systematic programming is not just using design recipe in the sense that I've explained it to you here, but also using abstraction systematically. And that's also an aspect, of course, where the functional programming aspects kind of shine. And then I'll try to tie that back to the list here. So I'm going to open another tab, and I'm going to add what's called a teach pack. That's just a library called the image teach pack. So, and you can see it down here. It says image.rkt, the image teach pack. So generally what we do what I do as the very first example, and this is at a point where people don't know design recipes yet, so this is before design recipe, is when we say, well, we know we can calculate with numbers, but we can also calculate with other things. And in particular, the teaching languages allow you to calculate with pictures. So you could, for example, so the image teach pack has, for example, has a function called circle, and you can do something like this. You can make a solid red circle that has this diameter. And what's kind of neat about the program, it's very simple on Dr. Racket, but the point is that the value returned by the circle function really is a picture. And when you ask for such a value in the REPL, it will just display it as a picture, right? If that makes any sense. So you can make I don't know, square one, which is also a square function. You could also write outline here, and you could write blue, and now you have a red circle, and you have the square. And we're used to, and maybe this also goes in Hans-Georg's direction a little bit more. Now, when you have two pictures, you can combine them, right? So, for example, you could, I don't know, image one. You could do this. You could say overlay, right? You could overlay circle one on top of square one. And that looks like this, right? So the idea is you take several pictures and you combine them into one picture, or images rather, right? And so this is the first inkling that we get at this point of the use of self-references, right? Because you use images to make images, and you can use that image to make more images. People don't generally notice the significance of this, but you can later backtrack to it. But picture is something that even kids can deal with. So sometimes we do like a girls' day at the office, where there's girls usually around 11, 12 come in, and they can certainly deal with these images within an hour or something like that. Now, there's also combinators called beside. There's also a combinator called beside. So I can take circle and a square, and they go next to each other. And now I could get this idea that I do it the other way around, like this. And I can then kind of combine them into a tile pattern like this, right? And everybody kind of gets that, right? And now imagine I'm like a tile layer. So I put tile into people's bathroom for a living. And I have this idea that, so somebody sees this pattern, right? But they say, well, could you make me the same pattern, but I don't want squares, I want stars, right? And so here's star. I want blue solid stars. And so here's star one. Star one. There it is, right? And so I could go and do the same pattern, doing it like star one, circle one, circle one, star one. So, that's the pattern I want, somebody might say. And now, you know how these things work, right? But as a matter of didactics, we can understand that really we don't want to have to explain what the pattern is every single time and always type above, beside, above, beside, above, beside. And now the neat thing in functional programming in general and in teaching languages in particular is, well, how do we generalize over those things, right? Well, the way we generalize is I copy this expression one last time, and I rename, right? So generalization. or abstraction. So we can say copy one last time and rename all the differences, right? Or rather, rename all the differences. So we might call these, image 1 and image 2. And here is image 2 and image 1. Of course, if we run that program, it's going to say image 1 and image 2 are unbound. But here is the point where we explain the concept of lambda. Image 2, and we can call this function, tile, for example. The indent. And then people can do, tile star 1, circle 1, tile star 1, square 1, and all of these things. So really quite early on, we explain this concept of abstraction, not as a general concept or something, but really as an activity, right? Abstraction is, you see two pieces of code that are similar, and that maybe are related in what they do. And what you do is as if you were printing them in overhead slides, you put them on top of each other, you look for differences, and each of those differences is replaced by a name, and each of these names goes into a lambda. It's a little bit more elaborate than that, but it really is also a kind of design recipe, or it's in the sense that it explains how to do abstraction systematically and mechanically. And again, that that makes that work in the classroom. Is that example clear? Okay, so the important thing is, right, in these teaching languages, abstraction almost always works with lambda. And I wish it were always, it kind of always works that way. I wish it were that way, but the way we can go back to that example with the lists here. And at some point, right, somebody says, well, we want to make a list not of numbers, but of armadillos, right? Or of, I don't know, whatever, of strings or of Boolean values or of animals or something like that, right? And so this natural desire arises. So we might make an A list where we say cons parrot 1, cons pillow 1, cons parrot 2, cons pillow 2, empty, The funny thing is, you do that, you get lots of signature violations, right? Just to reinforce the point that we're not dealing with types, but you get a perfectly fine list, right? It tells you violated signatures, but it nevertheless runs the program. So in order to do this abstraction, again, it's a systematic activity. Here, I mean, we've done it at this point in class, we've done it many times before, but we can, with the students, we can go, well, where does it say that it has to be a number? And it says, well, that's here. And we said when we're doing abstraction, we need to put in a different name, right? Sometimes it's numbers, sometimes it's animals, so we need to put in a different name. It has to be element, and element has to be bound somewhere. And in order to do that, unfortunately, there's this one point where I can't use a regular lambda. I need to use special syntax where I call this, I'm just going to call this cons off element. So it creates an abstraction. And I can then go and say, well, here it also says number, right? And I can just say, right, I need to replace the cons list by cons off number. So this is straightforward refactoring, if you will. And I can just, I'm sorry, not cons of number, but cons of element. And I can here use a regular lambda for doing the abstraction. And then somebody will say, oh, there's one place left where it says list of numbers, where we can just say list of element here. And now we've abstracted everything over number. You run the program, and it says, oh, list of number is undefined. But we can go, list of number is the signature, that is list of number. And then everything passes. And this is, again, relevant if you're transitioning to something like OCaml or Haskell later, because eventually you're going to get to the point where you explain a type variable. But here in these teaching languages, since signatures are regular values, you can just explain it in terms of the abstraction that they already know. And that I found to work particularly well when you have very little time, which is what I usually have in professional training, right? Is you can go through this quite quickly, and then later you can say, oh, okay, now we have type parameters in OCaml or Haskell, and this goes back to the concept that you saw here. Sometimes people will also say, oh, now I recognize this concept because I know Java, and there's this generics concept. Now I understand that kind of the angle brackets there are also a form of type level function. But here it's really explained in terms of the basic concepts that the students already know. Does that make sense? Okay, good. So I wish, one thing that is still on my list, but I haven't figured out how to do that, is really to have this thing. I wish this were implicit lambda, but I haven't figured out how to do that. Because there's always, so admittedly, there's always kind of a bump in the road when trying to explain that. And I kind of have to hand wave a little bit and say, well, actually what happens is define record gets translated into something where it will put the lambda for you. But I'm not happy with that. And it's always, we usually get over that hump, but it's not the part that makes me happiest. Okay. Any questions so far or any remarks? So, but I hope you'll recognize, right, that then higher order functions are then a straightforward application of the systematic abstraction technique. We could go through that if you like, but that really allows us to explain everything in terms of these systematic basic things. Nobody has a question or remark or challenge to anything here. One thing maybe that we noticed over time was really that introducing recursion this way really means that everybody gets recursion in the class. So that's never a problem, which is opposed to sort of more traditional classes in my, when I was younger, where recursion was this big and difficult thing, right? And where it was always common knowledge that not all students would get recursion, whatever that means, right? And so this technique here really means that recursion is not a particular challenge for students. On the other hand, and I mentioned this earlier, right, is this issue of compound. So the biggest hump really in class, I would say, is still this issue of doing compound data and of distinguishing compound data and mixed data, right? Even though it's much more, it's more primitive concepts that work there. And so, but recursion here is a complete non-problem. What else can I do for you? Finally, a red dot appears. So let us ask about higher order functions. So yeah, good. So okay, yeah. So let me try to find the point. So again, I mean, higher order functions are not kind of I mean, they're not a goal in and of itself, right? They emerge. The idea is to make them emerge out of the systematic techniques that we've seen at this point. Usually what I do is this. I kind of foreshadow what's happening by saying, well, usually as a small exercise or something like that, we've written a function where you add all the numbers. Now you write a function where you multiply all the numbers, right? And that ends up, I'm going to just very briefly do this, right? And you can already see this, right? It's a lot of tedious typing. So here's the template, right? And again, it goes first list, list product, best list. So here's the template. And then we eventually get to the point where you plug in the 1 here and you put in the multiplication here. Now, what you can already do at this point is you can everybody in class can see, well, these functions are very similar. They share all of their structure. There's only 2 tiny points of differences, right? So here's 1 point, here's one difference, right? And here is a difference, right? These two functions are only different in those two, and there's those 2 places. And of course, that is foreshadowing fold. And usually I then say, well, we're going to get back to that because it's a little bit more involved than we think at this point. We're just going to do something simpler. So there's lots of real world, domain settings that you can have. You could plan a dinner, and you might have attendees, and some of whom prefer vegetarian food or something like that, where you say, well, really, so you might have something like, why don't we do that example, right? So we have guests. So a guest has the following properties: name and is vegetarian. Right? Of course, that translates. I'm just going to go over this very quickly, right? We have a guest, right? We have name guest. We have guest name, that's a string, and guest vegetarian, which is a boolean. P1 make guest like true. Something like that. We have 2 guests, right? It's a vegetarian. So forgive me that I'm thinking that's a property of a person, not just a behavior. So at this point, we might say, okay, so here is a list, right? Guests. We could even put in a signature if we like, right? Guests, list of guests. That works now. And I can say cons G1, cons G2, empty. And it would be nice to have more elements. And then we could just say, well, extract all the vegetarian guests from a list, right? That would be a purpose statement that you could do. And so like that, right? This, right? We could say list of guest, list of guest. So, and at this point, again, at this point in the curriculum, right, people have lots of experience writing list functions, so this is no problem at all. And so here's the test, vegetarians guess, and we would expect cons G1 empty to be the result. So, and again, at this point, people are kind of tired of it, but we make them write it out a couple more times. We write, this template. Again, the template is something you write it down, you type it in without thinking, right? It's always the same. Cons guests, then we have first of guest, then we have rest of guest. You usually hear me talking like this in class as well, so that people get properly bored and in the right mood. And here's the self-reference. So that's where the recursive call needs to be, right? And then sure enough, people can say, well, there are no guests and there are no vegetarian guests either. And they get to the point where they say, well, if, so obviously what's relevant about the first one is whether it's vegetarian. You have a Boolean. Whenever you have a Boolean, there's only one thing you can do with a Boolean. You stick it into a binary, what is this? Into a binary conditional, which is called if. And you say, well, in this case, we have the vegetarians among the rest of the guests, but we also need to have the first one be included in that list. So we need to write first guest in this and write this. Okay. So I'm just kind of talking myself through it, but this is something that students can generally do, is they can write this extract vegetarians function. And you might also get like another function where it says extract all the, this is kind of contrived, but you could also have something less contrived, but extract all the even numbers from a list, right? Where you say extract evens, right? And here it's a list of integer. And then here's a test, extract evens. There we go. We expect 2 and 4 to be in there. And, you know, it helps to be a good typer at this point. And first numbers, rest numbers, recursive call, where the self-reference is, and eventually get to the point where you go with even. There's a built-in function that is called even, and where you go I hope you can forgive me that I kind of galloped through this because I'm trying to get at a different point. Now, the question was, how do we get to the higher order stuff? Well, if we look at those two functions, we can again see that they're very similar, right? We can see that they only differ, well, in the choice of name here. But most of the structure of those two functions is the same. So we can now apply this thing that I showed you with the tiles and you know, go through those motions here. So we copy that function one last time. When we do this, when we copy a definition, we need to think of a new name. So we're just going to call that extract. And there's a special rule. There's a special thing in the design recipe where it says, well, if you have recursive call, you need to rename those as well. And now we have a copy. And now we look for the differences between those two functions, right? And the differences are, well, the only difference that they have is it says even p here and has vegetarian guest here, right? And so we might, so very mechanically, we replace this by p and put this in the lambda, and we're done. Right? So that is this aspect, right? Is now we have an abstract function here that was created because we had two examples, right? So we're not trying to create abstraction prematurely. We have two examples. We have this very systematic procedure that leads us to an abstracted version of it. And again, this is something that students then are able to do for map or any or all or any function that you might choose to do after that. What you can also do at this point is that you can put the two signatures next to each other, right? So you could take this signature, copy it, and try to, and then you realize, oh, okay, so the function is called extract, but of course it shouldn't say guest here, right? It says something else, and introduce a signature variable at this point. So this is the next step after the higher order abstraction, is you also do an abstraction at the at this level, and in the teaching languages, the signature variables look like this with a % in the beginning. Usually this is quite seamless. So I haven't seen students get into big trouble at this point, right? If you focus on the systematic construction of these functions rather than trying to explain, rather than trying to explain what a higher order function is. Of course, then I'll probably notice that I've left out an important point, is that I haven't written down the signature for P, and that's usually a good place for a class discussion or something like that, where you figure out that, well, P, it's got to be the signature that is in common between even P and vegetarian guest. And you eventually get to the point where you say this has to be element to Boolean. You can derive this by going from even P, right? Goes from integer to Boolean. And what was it? Vegetarian guest. I'm sure I've done lots of stuff wrong. Oh. It's called, sure, it's called guest vegetarian. Oh. Not extract events. I'll extract events. Getting there. Check failure. So just to give you an idea, guess the vegetarian, first guess. So it's this test here, caused by this. Honest mistake. I don't know what's going on. Oh, it says cons. So it says here, I had this record. I had a cons off record. All conditions here yielded false, and that's because I wrote guest here instead of guests. So still, and I did that in a couple other places. I've done that one before. So now it all passes. Does that, Lena, does that explain a little bit what that approach is? So again, the approach is constructive, right? We're not making a big thing out of higher order functions. We're just telling people how to write functions, how to apply systematic abstraction, and that application of systematic abstraction is something that they've already seen essentially in the first 1 or 2 hours of class, and that tends to work pretty well, right? The only, as I said, the only part that I'm not happy about is really this, and that is also noticeable in class, is this thing where we introduce that. I'm sorry, whoops. Is this part here. That part I'd like to do better, but I haven't been able to figure that out yet, and it's taken me many years of thinking about it. Chat says, Leonard says it makes sense. That's great. All right. I think we're reaching the end. So as I said, right, if you're interested in that approach to teaching, if you're, well, if you speak English, then obviously check out How to Design Programs. If you speak German, I encourage you to check out the Dein Programm book, even though it's not completely finished yet, but maybe it might be finished before you're finished reading. I'm always very happy to hear feedback. Also, of course, especially feedback from actually using this in class and maybe encountering problems. The most, as I think, really the thing that is most important, that also makes me sad, is just how little educators benefit from each other's experience, right? Everybody tends to do their own thing. And that sometimes makes me a little sad, especially and I hope somebody will benefit from this, because specifically Matthias's group, and I guess I too now with age have just gained a lot of experience from using this in the classroom and from making the appropriate iterations and improvements, and hopefully reaching a point that works for a lot of people. So at the university, so to give you some other reference points, so at the University of Tübingen, I think 3 or 4 different professors have taught this in the past 10 years or something like that. So it's an approach that also is not dependent on the particular excitement level of a particular teacher. At least I remember at least one teacher who was grateful of having somebody else's material at their disposal, but who was completely non-excited about it. And it was very ungratifying for me that his results were just the same quality as mine. So it really, the quality of the material and the approach that you're using really matters. It's not just the person teaching. Any other questions or remarks? All right, then I guess we'll close this tutorial. Many thanks for everybody who was here, who asked questions. Appreciate your input. And well, ICFP, there's still a long week ahead. I hope to see some of you there. Stop by in a chat or in the lounge or something as soon as everybody's figured out how this place works. And have a great ICFP, everybody.